Okay, good afternoon. So, any questions? So thus far, I have had those of you waiting for PTs. I've had one person drop out, so unfortunately, still not at the threshold. But I am hoping more will. Almost always that happens. So um, hang on for another couple of classes before things get a bit clearer.
How soon do we need that board? I forgot what it's called.
Um, we are hoping to hand out the first homework this week. Okay. It, depending upon where you are shopping, it may take.
Yeah, I bought it last night.
You did, okay, yeah. A very simple homework. We have. I think my student is ready with all the specs, so we were hoping to hand it out in a day or two. Okay. It's super simple, so and we'll give you sufficient lead time. Again, kind of the idea is you can use it as a filter. You can always again borrow from me. Where did you buy it from? Just curious.
I bought it from ST.
Okay. How much was it?
22, but $10 shipping, so
$10 shipping, yeah. The
problem.
Huh?
Like newwalk.com.
You
don't have any shipping.
New what?
Yeah.
Oh, new egg.
Yeah.
New egg. And what's the price?
Yeah.
No, what's the price then?
Because like price $23 and no shipping. That's a big time.
$20 and no shipping.
23 and no shipping.
Okay. And new egg is local, so the shipping would be pretty fast. Okay, so new egg.
It's overnight for free on Arrow.
Okay. Well, on Piazza you can recommend things. Obviously, I order from Mauser and they charge a lot for shipping, and so I wish I had known. Okay. So anyway, you should be. So
Do you need the one that's first number or just
no, just an. Yeah. And does it come with the USB cable? Yeah, it does. Okay, cool. Any other questions?
what time would we be able to if we want to check out?
Pardon me?
If we want to borrow one,
Come during the office hours, which are today. Okay. I still have to. The only problem is I've not prepared the sheet to give you that I've received $25 from you. So, but I'll probably just do it right after the class. And okay. Any other questions?
So will the topics, the potential topics for projects?
Pardon me?
So will the topics?
Yeah, actually, I'll do it right after class. We have a whole set of projects. Okay. But it's not the final list. So you'll have to keep checking periodically. But other questions? Okay, cool. So last time around, towards the end, I was talking about that how these systems are organized in these three layers, kind of embedded or wearable or implantable, increasingly in some cases. Sort of these are the tiny devices. Then somewhere a device often referred to as a gateway class device, which is where you get more computing, but more importantly, connectivity, and then finally a lot of stuff happening increasingly in the cloud, both for inferencing as well as more sophisticated control. And in many applications, besides computing, is also the storage and the fact that this is the earliest place where you have data from multiple places coming together. So like for example, let's say you're doing a medical study and you're trying to build a model which makes use of data from multiple individuals, then likely the only place where you can look at the data together to then train a machine learning model would probably be somewhere out there. In settings like homes and all, your gateway can act as an aggregator, so it's possible that some machine learning kind of stuff can happen at the gateway device, or in case of wearables and all, you could imagine that multiple sensors on your body feeding data to the phone, and then the phone is where aggregation is happening. So there's a depending upon application, different kind of scenarios are possible, and these layers certainly overlap. But this is nevertheless a reasonable way of thinking about this. I pointed out that gateways are sort of really an artifact of that. It's very hard to design sensors and edge devices which simultaneously meet all the requirements of size and battery life and at the same time connectivity and processing. So oftentimes kind of divvying it up into those two layers is what ends up happening. And but again, sort of the constant flux in that direction. One of the key enablers in recent years really has been that lots of attention has been paid to devices or processors which are specifically targeting these devices. So it used to be that embedded processors were kind of like an afterthought, and oftentimes, in fact, if you look until even early 2000s, the embedded processors were always a few generations behind technology-wise. Namely, Intel would, for example, use the latest semiconductor technology for x86 processors, but your microcontrollers and embedded processors were 2 or 3 generations behind. That certainly has changed in recent years because partly for reasons of power, partly for reasons of size, and so your embedded class devices now often are also the ones pushing the technology. So like a chip on your smartphones and all are basically in the same generation as the full-blown processors. I think another thing which is happening, more relevant in a commercial setting, is this kind of emergence of, loosely speaking, the so-called maker culture. But really, what's pointing out is that a few things have changed. First, there's a manufacturing chain which has emerged, mostly situated in China, where you have an idea, and just like previously, you could kind of software was always easy to hack, but now you can do the same thing for a complete sort of system which has electronics, the mechanics, the software, and some very sort of well organized manufacturing chain. There are companies out here to which you can just submit your design and they take care of orchestrating everything, and a few days later your finished product arises. So it's become almost very easy to kind of take an entire, all the constituents of a IoT type device and sort of go with that. It obviously has ramifications on the way, the kind of things we can do in academic settings, but that's almost besides the point. What this has encouraged is that if you're a startup and all, you can really kind of start creating complete products, use them to show off, raise money, and the other model is the crowdsourced model, which is you have a few prototypes and then you start getting money and then build on the brand. So there are lots of companies which kind of do that, and some of them are American companies. They then behind the scenes hide the complexity of dealing with companies in China from you. But then you can also, there are companies like Seed Studio and all which could work that way. The whole process is pretty amazing. I mean, I used to buy parts from some of the companies out here, and then I don't know, many of you are probably familiar with Seed Studio, and I find it pretty amazing that I can order something and somehow magically the shipping happens very quickly, even though the whole setup. So I think they probably pre-stock some stuff in the US to kind of deliver stuff. I guess the main thing is it's very easy to prototype things now, and I mentioned last time around that how now even at the level of a processor, we have RISC-V and all, which are very competitive. In fact, in many cases, it's better than the ARM processor. So every aspect of your system, chip to sort of the board and software and everything, you can kind of rapidly prototype and the mechanics around it. So in many places now you see courses and all which integrate all these elements together. I think you see November 13th in the EE seminar, the speaker is Professor Bjorn Hartman. He's the director at Berkeley. Berkeley has this design, it's called Jacobs Innovation Institute or Design Institute or something like that. But it's basically a whole research center dedicated to developing design methodologies which integrate all literally kind of design all mechanical aspects. If you are so inclined, you can make a PCB in-house. These are all very cost-effective things at this stage. And I already mentioned a whole bunch of services, but besides that, you have, just like you have open source software, there is open source hardware course that you can download. You can design entire processors, peripherals, take an FPGA board, put stuff on that, or you get a chip fabricated. There are companies whose specialty is that they aggregate chip designs from multiple places and then run it through TSMC or one of these vendors. So all these pathways are open, and the main thing is that rapid turnaround and in a fairly affordable manner. And the consequence is that the kind of polished projects that we begin to see in like typical undergrad capstone design courses and all, are pretty interesting in the sense that they bring together everything. So I just picked up something from the undergrad design project at Berkeley, where these guys were designing kind of a smart flask or liquid holder, and it had sensors and stuff like that, but the finished product was everything integrated with the mechanics and all these kind of things, not sort of stuff hanging around and all, very polished looking things. And increasing in IoT kind of thing, it matters a lot for reason which is the following, that a lot of these devices we are designing for use by humans. And the way we, if you are going to train a model on data that you collect and all, it's going to be impacted by how it is received. So if a device is clumsy and whatnot, then it will not be used in the manner where it eventually would. So the data you will get will not necessarily be representative. So the moment we are dealing with kind of these human cyber physical systems, one has to begin to pay attention to the ergonomics of your prototype and the user interface of your prototype, because otherwise what you learn from it might not correspond to what a real deployment might look like. So there's a lot of stuff you can do, and there's a makerspace which is being put together here also. We're sort of behind some of the other schools in that regard, but hopefully very soon kind of courses out here would have same kind of thing. Individual labs do. So like for example, my lab has two of the items on the preceding list, laser cutter and 3D printer. Actually, we don't have PCB milling, but we do have a machine where 2-layer boards we can literally sort of just send out to print, and then it can put solder paste and stuff like that. So there's a lot of technologies which have come together to help out in rapid prototyping. Another aspect behind IoT is obviously they communicate, and so another area where lots of action has been happening is technologies which let these devices network with each other or network with connect back to the internet, and there are sort of several different overlapping technologies. And much of the action has been happening on the wireless side. But if you currently kind of look at what kind of things are out there, so firstly, for a lot of stuff, we simply use Bluetooth. And I think one big change which happened a few years ago was the emergence of so-called BTLE, which is the low energy version of Bluetooth, which is heavily duty cycled so that the power consumption is lower, and that kind of replaced a mishmash of other technologies, proprietary technologies that existed. Another reason behind it, which made it very successful, also was that iPhone never made classic Bluetooth, as it is called, one which was open to app developers or hardware developers. So if you were designing a sensor which used the so-called serial profile over Bluetooth, then on the Apple side of things, you needed expensive chip that had to be licensed by Apple, and it has some cryptographic features in it. So the market never built up. But then when BTLE came, so the way BTLE works is it's extremely low rate. In one of the lectures, I'm going to dive a bit deeper into it. but it basically was designed to send data over what used to be the beaconing packets in the original Bluetooth, in the classic Bluetooth. Point is, for applications like heart rate monitors and these kind of things, the data rate that BTLE provided was sufficient, and Apple also made it open. So suddenly, all across the smartphone ecosystem, you could design a piece of hardware and arrange for it to talk to your phone, and as long as your data rates were in the order of hertz or tens of hertz, you were good to go. So over the past few years, then suddenly there's a blossoming of devices which talk to your phone. They emerged, as well as so not just wearable devices, but things in your home, and also smart locks and outlets and things like that. So whole bunch of stuff happened around BTLE. But BTLE still caters to the market where you have a sensor talking to some smartphone type device, or some sort of a host. The more recent change, which my slide doesn't reflect, is the emergence of Bluetooth 5.0. Some of you may have heard about it. And one of the things that they have introduced is that it can multi-hop. Okay, so basically you can have the sensor talking kind of to another sensor, and therefore going over multiple hops to eventually talk to the phone. So it begins to look like some of the other technologies, but it will, as it penetrates, and we are just seeing the emergence of phones with that capability. So Samsung's S8 series and Apple's iPhone 8 and X, they all have BTLE5. So the penetration of Bluetooth will sort of go further. But in the same space, there are a bunch of other technologies that also play out. So there's something called ZigBee, or actually the underlying standard is something called IEEE 802.15.4. You can the main it's designed for a higher data rate and those sort of settings. But the main thing is that through this ZigBee consortium, it allows for these networks of devices where there's no central coordinator. In the sense, they create a ad hoc network. And this technology has gotten adopted for smart lighting and these kind of applications. So if you buy those Philips light bulb or a whole bunch of these LED bulbs which have emerged, they under the hood use ZigBee. ZigBee is also being used in a lot of smart meters, which then talk to appliances in your home. A lot of these fridges and washing machines and all, which have come up, which can connect back to your smart meter. They are using that. Then Wi-Fi has always been around. The problem with Wi-Fi is that it's much higher power consumption, but there has always been attempts at reducing that power consumption. And there were also things like Wi-Fi Direct, which is built into a lot of devices, which let peer-to-peer kind of connection. So my phone can talk to your phone using Wi-Fi Direct. But penetration on the sensing side has been thin. And oftentimes you do find sensors and all, but they're very clumsily done. So like your sensor may have the capability of doing Wi-Fi, but then it may act as a Wi-Fi access point, and then you're supposed to connect to it. Or cameras often do this thing, like the camera will appear as a Wi-Fi access point, and your phone is supposed to connect back to that. So the usage model has not been very nice around. And the another new kid on the block is the so-called LTE Direct. So LTE is obviously the cellular connection on your phones, but LTE Direct is being used for phones to talk to each other, again in a fashion which is power efficient and all. And Qualcomm claims numbers and all that it is better than Wi-Fi Direct and all. So we're really pushing it as a wireless technology for IoT devices to kind of adopt. And there are a bunch of other ones which I have not mentioned. Later on, I'll have a lecture where we'll just go through some of these technologies and their trade-off. There's another one called LoRa, which is again used for urban scale things. There's something called ESRC, which is used for your cars to talk to sensors or cars to talk to other cars. So there are a bunch of these domain-specific technologies that exist. Related to this is also, what happens on the side is not simply the communication protocol, also the whole stuff above which is built on top of that. So one area which for a number of years people have tried to do is the following: my device wakes up on a network. How can it all self-organize? How can I discover other devices? So there's always been this dream that devices can discover each other. They can figure out who can talk to whom, or all those kind of things. And there have been attempts almost every decade towards that. So back in 90s, there were some standards which have emerged, but the rest of the technology wasn't there. Again, attempts happened some years later. And more recently, there have been things like there's something called All-Seas Alliance. So it's something that Qualcomm has been pushing, or at least started. And kind of the idea is that on a network, devices make themselves visible, and so that you can discover. So you can say, are there any temperature sensors accompanied? Okay, and then they will return their attributes, and then you can connect with them and partner with them. So all sort of self-discovery, resource discovery, and these kind of things begin to happen. And there are other similar efforts which have been happening, including academic efforts. So there's a big project which UCLA has been leading, Professor Zhang's group and CS, and it's something called Name Data Networking. And anyone heard of it? Name Data Networking? Okay. So the concept is the following. Currently on the internet, when you need to look for some resource, let's say some data. So what do we do? Firstly, presumably there would be some sort of, you probably go to some sort of place where you can search, so it could be Google or something like that, or there is a search engine for IoT devices called Shodan, okay? It's actually a lot more than just a search engine, but point is somehow through some application level trickery, you are going to identify somewhere a resource exists. A very common way of representing resources is as a URI or URL, or a more general term is URN. So kind of looks like a common web URL. So you get that, then now you need to access it. Well, the first part is the host name. So you use the host name to then go to DNS server to get the IP address. Then once you have the IP address, then using the remaining part of that resource name, which basically is going to be handled by the destination device, you're going to send a packet which carries that information. The packet is going to be routed to the internet using IP routing. It reaches the destination host. It looks at it, says, okay, you are trying to access this particular sensor. Here is a reading, and then the response comes back. The problem in this whole scenario is that there are multiple rounds of network communication happening. The first time I have to search, I have to find some way of looking for the resource. Then I have to do this DNS query, and then finally I have to do the actual packet sending. So another way of structuring networks that people have often been pursuing is the so-called information-centric networks. And kind of the idea is that I can just name the information I want. So there is somehow magically everyone understands some sort of a language in which names can be expressed. So I can say, I'm looking for temperature on temperature in UCLA hospital area. Okay, so I can give these attributes, and that's the name. So instead of saying whatever www.ucla.edu, I define the data that I need, and the network somehow understands it, and then it will go around. As it routes the packet, it looks for searching the data. Okay, so the name basically becomes the primary way that you follow things. So NDN is Professor Zhang's effort. NDN is a new internet architecture which is based around this concept. That is, you route things by naming stuff. You name a value you need, or you name an action that you want, and then that's the lowest level primitive on which the network is operating. Time will tell whether it succeeds or not, but bigger point is that people are working on these kind of things, partly because the classical way of doing things where all these multiple rounds, but that aside, just discovering things is these are painful stuff like which sensor has the temperature in this room in Polter Hall. Finding that information is not easy in a conventional kind of a framework. So IoT architectures are kind of exploring these alternatives quite a bit as well. And needless to say, consumer electronic companies and all, a lot of them are in this game. Also, any of you heard of like Apple's HomeKit, for example? Some of you, right? Okay, who might be using those kind of products. HomeKit is actually nothing but really a networking standard which has been defined where devices can discover each other without you having to kind of tell them. So like Apple TV, which is used as the hub of HomeKit, can essentially broadcast a message within the home network to discover stuff. Is there a lock there? Is there a light bulb there? And it can aggregate that information. So without you having to kind of tell that, oh, that's the light bulb. But there's a lot more still going on. While it can discover light bulbs, but it won't have an easy way of saying, where is that light bulb? Is that the light bulb in my bathroom or in my kitchen? So there's a lot more still sort of uncertain as to what will happen, but the eventual idea is that if all these technologies achieve their vision, that devices know their context. So a temperature sensor that I put here, through its sensors will know that sitting in this location. Of course, it knows a temperature sensor, and then when someone is discovering that, looking for that information, that pairing will happen. And I won't have to anywhere name that the temperature sensor for room 5436 has this particular IP address. Okay, all of that gets automatically sort of part of the network. So HomeKit is an example. There are similar other attempts. Google has its own thing, and I've never figured out how Amazon Echo is doing this kind of discovery, but it also seems to have some similar feature where you can say discover all the smart home devices, and it kind of looks through your local network and finds what are all the devices and discovers them. So discovery of resources becomes very integral when you have these kind of networks where there are lots and lots of devices. Okay, so manual configuration is just not scalable. Okay, so one key aspect of embedded devices is that unlike general purpose computers, which kind of interact with humans, and one of the things about humans is that at least in most settings, we are very delay tolerant. Okay, so type something into Word, and if it takes a bit long to respond, that's fine. It's not catastrophic. We adapt. But when the computer system is interacting with physical processes, then there's a lot more rigidity, because on the other side is something which is not going to wait for you. Okay, and even in human context, oftentimes you can't, right? I mean, in medical applications and all. So the way computing is viewed in embedded systems often is in an event-driven manner. Now, I don't want to imply that that's the only place where event-driven stuff happens, but the view is that normally computing, the way we organize is some transformation. I have data, we compute some function over it, I'm interested in its result. And unless you are looking at very low-level hardware, that's the view we take. Compile a file, sort of do those kind of things. But moment you begin to interact with the external world, you begin to organize computing differently in an event-driven manner. So kind of the idea is that external world somehow, the change of state in the external world results in some event, and I'm going to organize my computation around it, and I'll have some timeliness requirements associated with it. So like my sensor reports that the car is going to hit the car in the front really soon, and then at that point in time you begin to interact. So one of the characteristics of embedded systems is that the computation is driven by what is happening in the environment, and a very common way of organizing this is in this event kind of architecture. But again, I would emphasize event type of architecture often is also encountered in more general purpose systems as well. A good Anyone wants to offer examples? Where do you think, where have you seen kind of event type programming being done, and why do we do it that way? And not standard programming. Anyone? No? So think about, for example, what might, so firstly, polling versus interrupt. Seen that in process?
Yes.
Why do we use one versus the other?
So if you want to wait, you'll poll. If you are waiting for the result, you poll. If you don't want to wait, you just go for the interrupt and it will stop anyways.
Right. So what's bad about polling? You're busy waiting. You're kind of spinning there, occupied, right? So interrupts make things more efficient, arguably. That is, I can do other stuff. Now think of applications where an interrupt kind of model gets used naturally this way. Keyboard presses, great example. Or any time human is interacting, so mouse click, stuff like that. And when you write graphics applications, if you go back sort of 90s and all, yes, there were operating systems which would poll for your looking for the mouse click and all, but that's not how we do it now. So we design functions and we tell the operating system, call it when there is a mouse event, or call this thing when there's a keyboard press, right? So that's an example of event-driven programming. Web servers operate the same way, right? I mean, it's not like they're continually sitting and polling. When a packet arrives looking for a particular URL, then you will, a particular function which is bound to it gets called. So this event way of looking at things is quite common because it frees up resources. And so it's present in general purpose things also, but it's far more dominant in when you're designing systems that are interacting with the physical world. So that's sort of one aspect. One thing which kind of distinguishes that many a times in systems on the embedded side, we may have harder time constraints, okay, in the sense that something, if I don't handle that event in a timely manner, then really bad things would happen, okay. Whereas in our user interface example and all, there's a laxity of timing, right? I mean, if the system is a bit sluggish in response to my mouse click, not really a big deal. So while so it's not simply reactive or kind of driven by events, but it's also there's a timeliness requirement, okay, which together characterizes embedded systems in sort of many cases. Again, you can always find instances of this in more general purpose setting. Games are a great example where the user experience takes a big hit if the system doesn't respond in a timely manner. Okay, so awareness of time or responsiveness of time and being event-driven is not unique to embedded systems, but is certainly far more prevalent in embedded systems. Okay. Another term that you would hear, therefore, is the concept of real time. So this is really an artifact of that the fact that there are hard timing constraints that exist in the system. So the word real time gets referred to kind of two different related concepts. So one is real time in the sense that I need to be able to keep up with the data. And that's very common in embedded systems because we often process streams of data coming in, video stream coming in or a sensor stream coming in. And usually the constraint here is of a type that after I've handled one piece of data, I need to make sure I'm ready for the next piece, right? So this is more like a rate requirement. I have data coming at me at a certain rate, and an implied timing requirement is that after I have handled dash number I need to finish it before dash number I plus 1 comes into play. And you can bring to bear pipelining and parallelism and these kind of things, but that's the basic goal. Keep up with the rate. And since many a times the type of sensors that we are dealing with are particularly high rate, image certainly is an example, but there are a bunch of other sensors which sort of throw at you lots of data. So oftentimes real time really means high rate data. But the more conventional meaning of real time is latency, which is something happened, an event happened, or could be arrival of a data or something like that, and I need to finish it within a certain tight bound, even though the next event may happen way in the future. So the example could be, it's not like your car hits a car in the front on a regular basis, but when it does, that once that rare event when it happens, you have a tight timing constraint on it. Otherwise, the application would not believe you to be correct. So this kind of real timeliness again is extremely prevalent and in embedded in CPU systems. And one way of thinking about it is that now we are dealing with situations where not only do I have to produce the correct value, but I also have to produce the correct value under certain timing constraints. And uh, so relative thing is real time does not mean fast. It just means predictability. That is, I want to meet some guarantee. So depending upon the application, the real timeliness might be at nanosecond scales or could be at second scales. Does not really matter. It's the predictability that we are really. So fast versus predictability, and the way you kind of end up thinking about this is that when you're designing these systems, your focus is on the worst case performance. So when we design general purpose computing systems, our focus tends to be on kind of the average performance or the throughput. So like for example, web server and all, you would care about how many queries I can handle per second, those sort of things. But so you focus on sort of stochastic averaging, but with many of these systems, your focus is on the worst case ability to meet your deadline. So the place where it shows up most, the place in a system where it affects things the most is the bottommost layer where you are scheduling resources, and you are scheduling the CPU time, and you are scheduling the communication link. So your mindset changes from giving good utilization to one where you want to give predictable deadlines. So a standard operating system, let's say Linux and all, they are trying to basically sort of be fair to different applications, give them an equitable share of the CPU, keep the CPU utilization high, those kind of things. Whereas the so-called real-time operating systems, on the other hand, make you promises about the deadline. So they basically say, so your contract with them might be something like the following: I have this function, and the data for this function is going to come every 10 seconds, and every time it comes, I want the OS to promise me that it will run and finish my function within half a second of the arrival of the data. Okay, so it's no longer just focused on throughput, but it's focused on responsiveness with tight requirements. So as you might imagine, mechanical systems and these kind of things often have these kind of constraints, because if you don't, then your outer system may go berserk in the sense that the control loop may, for example, not stabilize or produce a performance difficulty. So real time in the sense of predictable deadline becomes extremely important. So all of these things come together, and so if you again go earlier days, sort of the focus used to be on this real timeliness, but then other things emerge. So we also worry about energy. Something over the past couple of decades, I would say, has gained in prominence to the extent that now it is extremely important, and you really cannot imagine a system now where you do not have power management, because and power management is intricately tied with the speed side of things, because so there are a couple of aspects out there. One is when you think of power management, obviously I want to keep power consumption low so that my battery can last longer, right? Or if you're looking at a larger system, it could simply be I want to be more green. What are the other reasons why we may want to do power management? So one is larger battery life, the other is being able to have a green badge. Can you think of some other reason? Yeah.
Smaller overall.
Okay, so smaller battery. Okay, good. What else?
Cost.
Hmm?
Cost.
Okay. Yeah, cost. No? Thermal, yeah. So that's actually that's what I was looking for. In fact, one of the key bottlenecks in low-end devices, smaller devices, is the thermal bottleneck. Because I may give you that magical battery which packs infinite energy, but you're burning that energy in a tiny volume, and so the temperature will go up. So it's not simply about energy density, it is really about how much heat you can remove, and of course there are limits on that. So therefore, how much energy you ought to burn becomes, and so our phones get hot and all. I mean, that's an example. But now imagine stuff which is maybe sitting implanted inside the brain. It has no place to go, right? I mean, so thermal management becomes an issue, and modern processors are increasingly designed so that they shut down or they throttle the frequency down. So on one hand, I'm talking about real time and all, but suddenly we are into this situation where, because of thermal reasons, the system may slow down and you don't have any control. So I'm making promises about deadlines, but my processor is effectively a variable speed processor being controlled by a thermal regulator at the hardware level. Okay, and if I override it, your chip will burn. Okay, so things, all these, like as a message is, all these things entangled together. Okay, you cannot look at one in isolation of the other. So the view now really is that whether you're looking at processor or networking, these things, fundamentally you're trying to kind of navigate the space of real timeliness combined with energy efficiency, and of course all these other metrics. But these two are very critical, and they play a role at every layer. I mean, whether it's a sensor or processor or memory, or all of these places. There's certain common ideas which have emerged, which um, I'll touch upon a little bit later on how you approach this. Looking at processing, so that usually is the very first decision that you may end up facing for IoT type devices and all. There are a whole bunch of choices, and they're complicated by the economics of manufacturing also. So let's say I'm designing a device. I mean, of course, I can go with a processor, programmable processor, uh, either kind of one of the mainstream processors or something more embedded. But there are a whole bunch of other choices. There are a variety of domain-specific processors. So these are processors which are specialized for specific domains. Digital signal processors, I'm sure all of you have heard of. Microcontrollers are basically like processors, but with lots of specialized IOs and all. Network processors, security processors. Then ASICs, or application-specific instruction processors. And what these things are is that you can design processors whose instruction set you control. So for example, maybe you can strip down some instructions, maybe you can introduce some extra instructions, and there are companies which specialize in these kind of things. So they basically tailor, you can, through design tools, you can tailor the processor and generate a new compiler for it, so, and a new OS for it, so kind of the whole package. Reconfigurable system on chips. These are basically hardware where there is a fair bit of configurability at the hardware level, the way things are wired up, but not necessarily at the level of FPGAs and gate arrays and designing your own chips. So these are all sort of things where some degree of hardware configuration is done. So a very common model with reconfigurable SoCs is that you'll have a chip which will have a processor, and it will be surrounded by some peripherals, but there will also be hardware which you can arbitrarily program. So you can design a new accelerator. So let's say you want to process sensor data using a neural network. Maybe the management is being done in the main processor, but maybe you're putting some computation for your neurons onto that hardware layer, custom designed just for that application. Now, all of these things, they end up, as you might imagine, as I'm going down, I'm creating higher and higher performance systems. So in terms of speed, I generally would end up improving going down, but not necessarily always. So one of the things that come into play is microprocessors are very high volume parts. So lots of money to be made. So there is a lot better technologies which get used out here. So these might be working with, let's say, 14 nanometer technology. Whereas by the time you start hitting microcontrollers and all, maybe not. Maybe you are still working with 50 nanometer or some kind of few generation old technology. But generally speaking, by specializing the processing, I can make speed or performance go up. Power tends to be the reverse, which is more general purpose the system, the worse off it is going to be in efficiency. Just think of, like, let's say you want to AND two words, two 32-bit words. In a processor, for it to do it, there's a whole machinery being brought to bear, right? I mean, instruction decoding and all that stuff, just to do something which you can do with 32 NAND gates, or 32 NAND gates, right? So if you're operating in this regime, you can have a lot more efficiencies. Cost is interesting. So if you are designing a high volume product, then your cost is going to be lower. If you're designing a low volume product, then your cost is going to be lower if you use commodity parts like processors. On the other hand, if just for that low volume product you were to design something specialized, then that non-recurrent cost will dominate and you'll be worse. On the other hand, when you have high volumes, then that non-recurrent cost disappears and you are better off sitting at discounted. So what kind of non-recurrent cost am I talking about? Like when you design a specialized hardware or specialized system, what kind of one-time cost do you have to pay?
R&D cost.
Okay, R&D cost. So design effort. If I'm using a processor, then my R&D cost is limited to software design because Intel already designed the processor for me, or ARM already designed it. Okay, so that's one. What else?
Tooling costs for your memories.
Yeah, tooling costs of masks which are used for making the chips and stuff like that. They are multiple millions of dollars. Okay, so if you're designing, whatever, you're a lab and you want to design something unit 100 quantity, it's just not viable, right? There are some ways around it. I was referring earlier on companies which make chips by pooling together multiple designs onto the same chip. So there's some ways around it, but still, generally speaking, tooling cost and these sort of things come into play. Training cost and all, if people are already familiar with writing software for processors versus for your own specialized design. So a lot of these things come into play. I guess generally speaking, you either have to have high volume or be whatever NSA or something like that, where you can afford custom stuff built just for that thing at sort of high volume. Another choice you would face in kind of the same regime is hardware versus software. So I think at a deeper level, if you think about it, hardware and software are just two ways of expressing your algorithm, right? Fundamentally, it's just the algorithm functionality that you are after. And this division of hardware and software is kind of artificial. After all, a processor is a piece of hardware, and then you run software on top of it, right? And you can certainly view a chip, a single-purpose chip, as a processor which is running a single program. I think one way I like to think about this thing is the following: that it's the multiplexing that is happening. If I think of a processor, then I can do, not only can I do multiple things on it, but if I choose to do multiple things on it, then I have to time share. So that's where OS comes into play. It gives the hardware to one task, flips over to another task. So I'm doing on the same hardware, I'm reusing it in different clock cycles for different purposes. On the other hand, a purely hardwired design, each operation is mapped to a separate piece of hardware that presumably gives a speed, but it also results in inefficiencies. That is, if particular AND operation in my algorithm is mapped to a particular AND gate, then that AND gate is going to lie idle most of the time, right? So multiplexing gives us efficiency. So this, what we call as software and hardware, is really the spectrum of choices we make, where each operation in my algorithm is mapped to its own dedicated hardware. That's what we think of as pure extreme of hardware. And the flip side is that I have some general purpose hardware unit, and then every operation is recycled on top of that through some smart scheduling, and that would be kind of a perfectly sequential processor. And then there are all sorts of choices in the middle, which give us different. And a related concept out here which comes up is concurrency. which is how much concurrency do I have in my system. So in my system at any given point in time, am I just doing one thing or am I doing multiple things in parallel? In software terms, you can think of multiple threads or processes running in parallel. In case of a purely hardwired design where each operation is mapped to individual piece of hardware, there is an implied parallelism, right? I mean, everything can run in parallel. So choose this two if they are independent. So the hardware versus software is kind of a fluid choice, driven in many cases by what is happening in this end of things. Final stuff that I want to mention is that life often gets even more complicated. So nowadays, you can take, let's say, an FPGA, and then you can take a processor design and map it on top of FPGA, right? So these things are called soft processors. So no longer is my processor hardwired, so to say, on the chip. So now I have software running on a soft processor, which is on an FPGA. So I have created yet another layer of reconfigurability, because I can replace that processor at another time by a different processor. I can fix bugs and all. But now I have programmability at two levels. I have programmability of the processor architecture, and I have programmability of the software running on that processor. So there's a rich space, and for different kind of projects or products, and at different phases of their maturity, you may adopt different things. It could be that in early phase, you go with a quick and dirty design and then kind of optimize it with something which is more hardwired. Okay, some other issues which are coming up with IoT kind of thing. So I mentioned time awareness, power, those sort of things. I think another new one which has gained a lot of attention now is security and privacy kind of challenges. I'll kind of I have a whole new course that I'm introducing on this, which I'll teach in winter under CE 209 AS. But just wanted to give you a glimpse of kind of issues that are coming up. So think of mobile health system. So we all use sensors and medical instruments and stuff like that, and there is a whole enterprise being created around this with all this data processed locally, processed out in the cloud, disseminated to different people and stuff like that. And as you can imagine, all these things have sort of variety of usual IT type problems, but there is also a set of problems which are unique to the fact that we are coupling with the system. So for example, tampering of sensors, spoofing of sensor data, or things you can infer from the sensor data. So besides the usual software, viruses, and stuff like that, there is a bunch of other stuff which happens in these systems because you are dealing with sensors and all. So some issues that are being addressed nowadays or people have concerns around. So one is you have sensor data from whatever, medical sensors or your home and stuff like that, but it's being processed in the cloud because our devices locally are not necessarily equipped for it. So can I create ways in which this data that I can gain services, but without letting the service provider, without the cloud component, seeing the data in clear text or plain text, that is not seeing the raw data. So, for example, Google sells these things called Nest Cams. These are cameras that you can deploy at various places, and what they do is they keep sending the images to Google's software in the cloud, and there they run some machine learning stuff, and then they send back notifications. But the notifications are not like the usual camera ones where it says, oh, there was motion and all. They are things like I saw a person, or the latest versions which have come out over the past 2-3 months. They can recognize faces, so they might say this is John or stuff like that. Okay, so now, but the only way they are able to provide these things is because it's sitting out there on Google servers. Question basically you're asking is, could we do it in a manner where Google never even gets to see the plain text image? Right now they do. Could we do it in a manner where we can still get the same service recognition in this case, but even the, that you have encrypted the sensor data with a key that only you know and no one else. Okay, so the data never goes out. Um, doesn't ever get visible to anyone else. So could we do something like that? And remember, what is not going to be acceptable is that Google has the key, because that's not what we are looking for. That kind of security we already have, because your data goes to Google through SSL interface, encrypted tunnel. So we are not protecting against someone hacking onto your communication link. We are worried about that we are relying on service providers with relatively intimate or privacy sensitive data. So, there are some approaches which are beginning to emerge which kind of provide that, and in that other course we want to talk about that. And this issue, as you can imagine, sort of occurs in many places. I mean, lots of data is being collected. Look at like Waze, for example, right? I mean, it's collecting data about locations of Waze users to be able to estimate traffic situation and then sort of guide the city scale traffic. But you are giving up your privacy. Okay, so or likewise, in this particular example, maybe it is something about identifying bad road segments. So the data is going from the cars, but again, could we organize this thing in a manner where individual sensors, their privacy is not lost, and yet we are able to make whatever inferences that we seek to do. So IoT applications are littered with these kind of trade-offs. One other thing is a lot of our gateway devices are on the wide open internet, and therefore they can get hacked into, and they often are. Sometimes so pretty much any device which is on the internet, if it's not carefully managed, is open to all sort of issues. I mean, bugs are discovered after the initial deployment. You have also these issues that a lot of these devices are really low-end manufactured devices, so they have simple passwords. Operating systems may never get patched and stuff like that. So security of devices in space is kind of partly simply that their cost structure doesn't allow them to be managed with the same degree of care and professionalism that you might expect with sort of servers and those kind of things. Let's see. Skip some slides. I just when it comes to sensory data, there is a fair bit of concern that you can make inferences from this data that were unexpected, and moreover, the very same tools of machine learning that help you make the desired inference are also something that the adversary has access to and can make inferences which you would never expected. So I've given a whole bunch of lists out here, can range from relatively innocuous and your reaction will be I don't care, to one where yeah, if you knew, and I think oftentimes it's just that it is not expected. So to give you an example or two, smart meters. So smart meters, they basically have a fairly high resolution sampling of the current being drawn by your home as well as the voltage that is being seen. And if you look at these signals, they capture a lot of information about what the appliances and devices in your home are doing. Using variety of machine learning techniques and all, you can begin to reverse engineer that. So in this particular example, some work out of Germany, and what these guys were doing was that they make use of the fact that the power consumption of big screen TVs is a function of the content being displayed. And the reason it's a function of the content being displayed is that many of these TVs, to optimize power, whenever areas of the screen are black, they turn off the backlighting, or in case of OLED type TVs, that's intrinsic to the design. They call this emissive technology. So now the content, essentially if you think of the video content as a signature, then that signature is riding on the power draw. and big screen TVs are, let's say, a couple of 100 watts. Okay, and so it's easily discernible on your smart meter side. And now using whatever signal processing and ML, you can kind of extract that. And moreover, you also have help. A lot of video content is out there. I mean, these are TV channels and movies and stuff like that. So you can pre-process content. So, like for example, if I'm after that, are you watching that particular movie? I can create the signature for that movie, and then I can try to see whether you are actually watching it. In case of live television, you TV guide tells you what are the channels which are on in your area, so you already have a narrower surface. So that's an example that kind of inferences that could be drawn with given adequate sort of power. But the bigger point is that it's very hard to protect sensory data. This is another example, and over the past couple of years, lots of people have been sort of doing this. So our phones have gyroscopes and accelerometers, right? That's what the name of inertial measurement unit. The way these chips work under the hood is that on the chip there is kind of a mechanical thing which kind of vibrates when under the right type of acceleration. But guess what? Sound waves are pressure waves. So when you speak or when there is sound, then those pressure waves are hitting those masses also, and therefore they are creating a signature. So people discovered that when there is sound, then your accelerometer on your phone reports data, and therefore you can use the accelerometer on your phone or gyroscope on the phone as a crude microphone. And by subjecting it to pretty elaborate machine learning type methods, you can begin to discover things. You can begin to sort of capture what was being said, or other things like uh, the gender of the speaker, identity of the speaker, these kind of things. Again, unexpected. The reverse is also true. Namely, you can use attacks these things. So a group from Korea showed that drones which use accelerometers and gyroscopes for their control action, if you bombard them with sound, targeted sound, then you can affect the readings of the IMU, and the drone can be made to crash or lose its way. Okay, so or another example, this was work out of Stanford a couple of years ago, which is the following: on your phones, the level of the battery. Um, so let me ask, if if you were faced with a decision that should you share the percentage battery level openly with an application, what kind of concerns would you have?
If your battery is high, it might just try to use, do more things that you don't want, because it thinks, oh, I have power.
Okay, so it can use resources. It can, I guess the other obvious one in that thing is your battery is high still at the end of the day, maybe you didn't do work. Okay, but what kind of, can you think of some more serious privacy implications?
It could, at night, you could see if your battery level is low and it starts charging and determine where your house is potentially.
How would it know that where your house is? So
So, I mean, based on where you charge the phone each day, like it would determine.
oh, okay. So yeah. So where I plug in the phone would reveal things, but that's the plug-in action. You're right, but just looking at it, yeah, yeah.
Do you have any for your using actually or using your using habits? When you use the cell phone, the battery is charged much faster than when you put the cell phone in the pocket or at night. So you may infer some using habits from your
Yeah, I guess that generally goes into, you can infer something about when you are working, possibly where you are working, but I guess that attack requires you to have access to GPS, but which is usually protected, right? So, but actually, it does, what the Stanford group showed was that from battery level trace alone and no access to GPS, they could infer the location of the phone. And the attack went like the following. Big part of power consumption of these phones is the cellular radio itself. Power consumed by the cellular radio depends upon how far it is from the base station. Okay, so now I begin to estimate the distance from the base station, and if I have some side information about you, that you live in LA or whatever, my search space is narrowed, and now you start sort of mapping it against known base station locations and begin to infer your location, knowing in particular that you are probably on a freeway or something like that.
So this is using the rate of battery drop-in, not just the current battery level.
Yeah, in this case, it would be the profile. Yeah. So anyway, I mean, when I first encountered that paper, it was like, yeah, it's pretty interesting attack. Yeah, so anyway, so I guess the point is that these kind of with sensors and actuators and all, you've got to be sort of careful there, and how do you protect against it? Okay, kind of becomes an issue, because it's not simply. I mean, I trust you when I'm giving you the sensor data for one purpose, but not for other purposes. And how do I manage that process? That's kind of the tricky part. Similar issues around actuators emerge. So like if you look at the overall control system, for example, you can have attacks happening at the sensor, you can have attacks happening at the actuator level. So actuators can be jammed, sensors can be spoofed. Some other attacks out here, okay, including some work in my group with Professor Tabuada and Digavi. So just to cite something. So for example, one of the attacks that we mounted was the following. Your cars have anti-lock brakes systems. That's pretty much every car has. To do that, to implement that, they sense the wheel speed. To sense the wheel speed, pretty much the way it is done is that axle and wheel, on one side there's a magnet and the other side there's a notched wheel. So you are basically measuring when the wheel rotates, there is a varying magnetic field, which looks like a sine wave, and then you are sensing that sine wave and look at its frequency, and that gives you the wheel speed. So that's totally how things work. What we did was that we basically used something akin to these noise cancelling headphones, where you cancel an acoustic field. Here we cancel the magnetic field and then overlay on our own field. So we have a tiny little electronic device, and these sensors are out in the open. You just go into the car and just put it, okay, and now we can change the wheel speed that your car thinks it's going at versus what the reality is, and then we can, obviously, by messing with that, we can cause the car to veer, and also we have some pretty cool attacks and all around that created. And then the problem becomes, really the problem is, in the face of these kind of attacks, can I design systems which are still robust to them? Okay. So again, bear in mind, this is no longer a problem one of just saying, okay, I can encrypt my way out of it. It's not, because your data is getting compromised before it comes into your system or after it leaves the system in case of actuators. The broader technical problem is called secure state estimation. That is, can I estimate the state of the world securely in the presence of these kind of attacks? Okay, and that's sort of the nature of things out there. So there are a whole bunch of these things which have emerged in recent years with relatively interesting type of attacks, including sure most of you would have heard of Stuxnet back many years ago, where the Iranian centrifuges were damaged. There's a group at Technion in Israel which does all sort of cool stuff with attacks on cyber physical systems, including fooling bays and things like that, where creative ways. So there's a whole bunch of stuff which is sort of happening. I'm going to skip the slides which related to the anti-lock brake, but main thing is then you need to begin to think of these systems with security as a first order consideration. Okay, and that basically means that measures which will be at the sensor actuator level measures. So just to give you an example, anytime you have a sensor which is a passive sensor, what I mean by that is it's just observing signals. It's very hard to protect, because the adversary can always manipulate with that signal. On the other hand, we have active sensors which send out energy and then look back at the energy which bounces back. A radar would be an example. So active sensors have some advantages. So one piece of work that some of my students did recently, the paper coming out next month, is a lot of these digital assistants which have emerged, right? Amazon Echo being an example. Thing is, you can give it a voice command and it will happily obey and purchase good for you, right? Okay, so now so far, okay, you say big deal. I'm the only person at my home. But then there are some attack papers which have emerged recently showing that how you can mount attacks on Echo type devices in a manner which is very hard to catch. So one example of this is the following. This is a group at Illinois. What they showed was that so if you look at a microphone, it has a band in which it is linear. So that's your normal hearable band. So it would be, let's say, something up to, let's say, 20 kilohertz, upper limit of human thing. But it's not that as if the microphone suddenly just stops there. It is still capturing things at the higher frequency, but those are non-linear. So what this group showed was that they could send out a signal in that ultrasound regime. Humans won't hear it, but these devices do. And it was designed in a specific manner so that the non-linearity, because remember when a device is a non-linear regime, then it basically has harmonics all over. Some of those things are going to fall into the audible domain. So these devices think they are hearing a audible command. So they would shape an ultrasound signal whose effect after interacting with the microphone would be such that the machine learning algorithms on the device thinks that you are giving a specific command in the normal human domain, but a person sitting in that room will not hear a thing. So these kind of hidden attacks where can now be mounted on these devices. There are a bunch of the other kind of things also. All of these things are under the name of adversarial inputs. That is, I can design inputs to your system which humans will not find anything fishy, but the device will act upon it and make a wrong decision. So I have another student of mine, we've been working in this area where systems which are designed to recognize objects in images. Okay, and again, work in recent times have shown that you can fool these. So your car may be seeing a stop sign there. You will think of it as a stop sign because it looks like a stop sign, but the vision system in your car will see it as something totally different. And you can design these things because deep down these are all systems which are making some decision, and by appropriately shaping the data, you can fool them. So this interface is actually ripe with opportunities both for attack and obviously coming up with defenses for them. And then then the system level measures where you design your control algorithms or decision-making algorithms in a manner which realizes that. So perhaps having enough redundancy, things like that, those sort of things come into play. So very sort of ripe area of sort of people doing lots and lots of work in this space. Okay, so bottom line then, what ultimately what you're trying to protect is this kind of sensing, inference, decision control kind of thing, and finally actuation, and all of these things can be attacked. And in all of these, you have a whole bunch of problems arising having to do with power, timeliness, security. All of these things come together, and then architectural issues like how do I think about the whole system like this? Where should what happen? Should I do stuff in the cloud, in the edges? What kind of things that we do? So my hope over the next few lectures is to walk through some of the topics. I used to cover security in this course, but because of the new course, I'm going to bump it up there. To replace it, what I'm doing is I'm going to be introducing some material on how machine learning gets used when processing in these systems and all, and some of the stuff on human coupling. So some new topics this time around. Starting. So that's what we'll do. So let's take a couple of minute break. I want to do the usual attendance thing. So um, uh, this time around, thanks to G, I have a QR code. So okay, but just again, you have time to clarify. I'll just bring some water. What software do you use? The website recommended Redshift or something like that. Did it work for you guys? Work for you? What software do you use? QS. Actually, as a project idea, so you know I'm organizing the ECE seminar also. How many of you are enrolled in that? No one? A few of you. Okay. The project idea I have the following: designing an attendance system which has the following attributes. Should be no paper sheet and all, but it also has to verify you are there and not proxying for your friend.
No, not making this for you.
Huh?
We're not making this.
You are my student, you better do. But I've been thinking about approaches to do it, some ideas, so remember, this is partly about spoofing, security attack on the system. Because right now, it's a chaotic system, there's a sheet and everyone just sort of goes after it, and then of course then students can disappear after signing in, so that becomes a problem. So I want an approach. So I've seen in some universities they hand out a secret code, but that doesn't help because students share the secret code, right? So it has to verify that you are in the room.
Donate iPhone apps.
Huh?
Donate iPhone apps. Like everyone should like have their face recognition for the Face ID.
Ah, okay. The only problem with that is that it will become a scaling problem, right? I mean, by the time you're done taking it in, let's say you buy one, okay? So it has to be something where I can assume that everyone has a phone. I can display something out there. I can have some piece of hardware in the room. I think there are obvious things like if the same phone submits two different things, then that's cheating attempt. But
Can you just have like a Bluetooth connection?
Yeah, so you make sure everyone is recognized by that particular device, so then when they walk in the room, then that particular address.
yeah, The problem is the following: that for privacy reasons, these devices don't advertise. Yeah, so there's a bit of a trickiness there. Yeah, I can hand out beacons, but the problem is. Okay. Uh-huh. Yeah, so I guess the assumption I basically have to make is that um, people who are skipping the class will not give their phone to their friend to take in, right? I mean, that's still an attack which is remaining.
Everyone has a card, like a UCLA
Uh-huh.
card, so you just have a scan of the card, you just tap it.
You won't give your friend your card if you're skipping the class,
I mean,
right? I mean,
Fingerprint ID.
so reliable, spoof-proof attendance mechanism. Okay, anyway. Weight of the classroom, yeah. No, so I can have a doormat which does some sort of recognition based upon your weight and height. Yeah, possible. Okay. Okay, so let's start. So the first topic I want to go over a little bit is into the platforms themselves, and what kind of issues and challenges and all are kind of arising in there. And then next time I'll also sort of cover a little bit about embed specifically, which you are going to be using. So generically speaking, a lot of these systems you can think of there is kind of a core computing, storage, memory kind of subsystem, but then it is surrounded by sensors, actuators, various ways of interacting with the network or other nearby devices. Very crucial, some sort of a power system, and then finally, usually some sort of off in some way for it to interact with the operator or a human user. So let's walk through some of these pieces and what kind of things are happening. So computing and storage is the first one, and we already saw that there are a bunch of choices when it comes to implementing this computing part, but very broadly, when you approach designing these kind of systems, they range from kind of essentially creating a customized, assembling a system at kind of a chassis level, at board level. So very common strategy is you buy these chassis which have buses which are meant specifically for use in these category of applications, and there are companies which sell boards, and you plug them in and you create a custom system. So National Instruments and is a big player in this kind of thing, but there are a whole bunch of other companies, and there's specialized buses. So like CPCI is compact PCI bus. PCI bus is the same bus that you find in your PCs, but CPCI is meant for kind of these more compact users. And usually, so you can think of these things as nothing but like your chassis for your cases for your PC, except these are designed to be more rugged and have some different buses and stuff like that going on. So that's one approach, and very commonly used and very common in factories and all, as well as kind of a lot of industrial usage as well. Standard ways of interconnecting boards, and you really, as a system designer, are just focusing on those board thing and then put some software on top of that. In a lot of other applications, you have to dive down. You are going to make your own board and perhaps even your own chip. And this is so on both of these things. So let's take the board part. There are companies now where they give you a menu of things in terms of processors and all, and you go to their website and you kind of configure stuff and put your credit card number in, and your board comes back a few days later. They take care of all the back-end stuff. So some of the embedded players have gotten into this. So one company whose which also sells sort of standalone Linux boards called gum sticks. So these are kind of gum stick sized kind of Linux computers, but they in recent times have gotten into the business of just customizing them for your need and creating something which just has the right type of interfaces and processor capability that you want. And then same thing at the chip level. When you design chips, you design these chips using cores, and you can buy cores. There are companies which sell professional quality cores, but there is, as I've shown in an earlier slide, there is a whole open hardware core community out there. And the other thing I mentioned was this kind of RISC-V, which has emerged as a professional quality processor, which lets you design things pretty much from scratch. The system on chips are these chips where you have some processor and all, but then you also have programmable digital hardware and also possibly programmable analog hardware. So Cypress Semiconductor sells these chips called PSOCs. Some of you may have used them. They're quite commonly used in undergrad courses also. But kind of the idea is that there is a simple processor with some memory and all. There is a programmable logic array for digital logic, and then there is also an analog subsystem with sort of op-amps and some passive stuff so that you can create filters and all as for the front end signal processing. So you can kind of create an entire system, and there are versions of these chips which also have a Bluetooth radio, and also you really have a self-contained system which is entirely programmable. So, and there are a bunch of sort of other things at higher end. So PSOC is kind of more low-end devices, but FPGA companies like Xilinx and all have kind of more elaborate systems out there. Most common is the use of so-called microcontroller units, or MCUs, which are really nothing but CPU cores with some on-chip memory, but lots of peripherals. So the difference between these and, let's say, the processor that you would have in more general purpose setting is that your CPU cores are simpler. Usually general purpose processors, the memory they have on chip is for cache, whereas in microcontroller, that's your main memory, and for data and some sort of flash or something like that for the program. And then lots of ways of interacting with the outside world. Okay, so as opposed to on, let's say, on a PC, the peripherals usually are separate chips on the board because the main processor is humongous enough. Here, you would have lots of things for interacting with sensors and actuators. And fortunately, there are a whole bunch of standard ways that have emerged to talk with a wide range of sensors and actuators. So what these things support are things like, besides the usual serial devices, you have things like I2C and SPI and CAN bus and pulse width modulated signals. And so these are ways in which you can talk to sensors, motors, actuators of different types, and all, and all be able to do it. There are some of them target specific segments like automotive and all, where there are even more specialized needs. But a general purpose MCU would at least provide you a reasonably wide set of things. The example is the embed board, for example. So the type of processor that embed board is using is an example of an MCU. Other characterizations out here would be that usually these things are sort of small CPU cores. So what I mean by that is it probably will not have fancy architectural features like multi-scalar and superscalar, multiple cores, deep pipelines. None of those things are there. These are relatively straightforward RISC processors designed for power efficiency and low power. So MCUs are the most common one, and there's a wide range of choices available. 8-bit, 16-bit, 32-bit, and also 64-bit. At the real high end, namely things going into your smartphone and Apple TVs and these kind of devices, you are beginning to see now 64-bit and multiple cores. So these do represent kind of the high end, and also some of them, because of the media they process, also have GPUs there. So the high end of these devices is getting significantly powerful. Also, NVIDIA makes embedded GPUs. So these are GPUs with some processor, and they are the kind of stuff like are being used in, let's say, Tesla's autopilot, and these kind of systems are using that. So what I'm showing is kind of more typical, but there is a high end which is extremely powerful. On the low end microcontrollers, there are the main culprits are companies like Atmel and Texas Instruments and a few others, ST Microelectronics. Thing to bear in mind is that most of these companies, when they are making processors, they are not making processors themselves. They're just licensing the core, and then they create a processor. They create an MCU by surrounding it with their own set of peripherals and all. So ARM is the company which is most into this business of licensing its cores to others, and then like ST Microelectronics, the M7 processor in it is nothing but they've licensed it, and then they create a whole bunch of different versions of the processor with different amount of memory and different types of peripherals and things like that. But they are not the only players. There are companies which have emerged which have been making low-end x86 compliant processors. So some companies in China have been doing that. So these are low-end Intel compliant processors that you could work with. Atmel makes both ARM processors, and then they also have their own processor, which they call it 80 mega, and they are very popular in a lot of products and all. TI MSP 430 is another processor which is TI designed, and it's well known for extreme power efficiency. It's one of the most power efficient processors which are out there. So there's a whole bunch of options and players sort of which exist, and usually when you go to these companies' website, it's not like there is one MSP 430. You will find like maybe a couple of dozen of them, and they'll all differ in RAM and ROM and peripheral set, and sometimes they're mated with radios and sort of various kind of things which go on. On the ARM side of things, so ARM has two distinct categories of families of core processors. So one is kind of the low-end stuff, which and they usually go in the Cortex M series things, and M7 is the high end within that low end. And then you have these processors which are being used in smartphones and all, which are things like A8, A15, A9, those kind of things. They range all over the map. Most companies who are making ARM processors literally take their design. So ARM gives them macro, which these guys just put onto the chip. But then there are also companies which are ARM architecture licensees. That is, they are allowed to make their own processor compliant with the ARM architecture, and Apple's chips, for example, are an example of that. They are designed by Apple from scratch. They are not following any standard ARM core, but they are instruction set compliant. Now, one of the things that you would encounter, one of the driving things in these things are the issues around power and energy, and a trade-off that you would often encounter is the trade-off that is how efficient is a processor to power manage versus how efficient it is in doing computation. So what I'm saying out here is the following, that we often loosely speak about this processor is low power, or this processor is more energy efficient, but there are many different ways of interpreting this. So what I have shown out here, so one way of interpreting is I have a MCU which consumes 10 milliwatt, and I have another one that when it runs consumes 100 milliwatt. But that doesn't necessarily mean that the first one is going to consume lower energy than the latter one, because that also depends upon what's the architecture of that chip is, right? So what we see out here is same computation being done on two types of processors. On the left-hand side, it is running on a low-end microcontroller, kind of a 10 milliwatt class on the right hand side, it is running on a ARM processor. These are old plots, so almost 10-year-old numbers, but the point still remains. This is like a watt type processor. So architecturally more sophisticated, pipelining, 32-bit, all that stuff on the right. And on the left is a simple microcontroller, couple of order of magnitude less power consumption, but simplistic architecture, 8-bit, and so on and so forth. So left is low processor, lower power, but on these things you can see it's much less energy efficient because execution energy is shown out here. So it's the product of the two that you have to care about: the power it consumes and the compute capability it has, which is a function of its architecture and stuff like that, right? And so it's kind of stating the obvious in a way, but that point often gets lost. Now, so that's in terms of how much energy it will take to do a computation. But that's not the only story also out here, because I'm not doing computation all the time. A lot of time my system is doing nothing. And in fact, if remember we said embedded systems are often event driven, and in many cases the event happens once in a blue moon. So it's not only important how efficient your system is when it is actually doing the work, it's also equally important how efficient your system is when it is not doing anything. The idle or sleep mode kind of thing. And that is where the heavier duty processor, which takes less energy, has its disadvantage. The disadvantage is that if you keep power up, the transistors are leaking energy. So there's a baseline power which is very high. So if you take one of these processors and if they are merely powered up, their power consumption may be more than this little processor out there, which was 10 milliwatts or so. So this just the penalty of powering up is huge. Then the other thing is, then when you have processors which are complicated, they also take time to reboot. They take more time to reboot. It's one thing to boot up a simple microcontroller in a few cycles, and it's entirely another thing for a heavier duty OS to boot up on a bigger processor. And likewise, when you're putting it back into idle or sleep mode, you have to save the state. The more state you have in your system, the longer it's going to take to preserve it. So while in terms of energy, the bigger processor, the one on the right, processor is very much better, but when it comes to sort of doing nothing, being vigilant, duty cycling, namely putting it to sort of an off state and making it up, then things become very different. So what you see out here is on the this is the ARM one, so suspend and make it up. It takes hundreds of microseconds. Order a couple of hundred microseconds, 100 microseconds or so. To boot up the OS takes milliseconds, not at all uncommon. I mean, your Linux type things and all of them are in that range. The sleep mode power consumption is in milliwatts, okay, which is 100 milliwatt range, which is of more than what sort of low-end microcontroller class things would consume. So now you are often faced with this thing that while you are active, you would probably prefer the big processor, but while you are doing nothing, you'll probably the processor, and while you are doing nothing, you'll probably prefer the smaller processor. And the same general concept actually applies to other things, radios, sensors, all of these things that you often face with this tension between that I can use a high-end stuff which will do bulk computation or bulk tasks very efficiently, but then the penalty of using it is very high, and that works to your disadvantage when you are doing nothing, so to say. In embedded systems, that kind of shows up once in a blue moon an event happens. When it does happen, I have to do a lot of heavy-duty processing, but it's happening rarely. So somehow you want to combine attributes of both of these. What do you think we can do? How can we combine attributes of both?
So you can have either like a co-processor or a component on your microcontroller that you can turn on or off. So let's say you're like, it's common with like floating point units. If you don't expect to do any floating point work, you can just cut power to the entire floating point unit and higher power consumption.
So yeah, so I have both, right? I mean, I somehow create an illusion of having having a processor which is both good at bulk processing and is good at rapidly waking up and all. And kind of the idea would be I'll keep my little guy on all the time, and then like they were suggesting, what we'll do is when I realize that I need the big horsepower, I'm going to kind of make it up. Okay, and that's loosely speaking. There are many different ways of structuring it. One is indeed what you're saying, but there are other ways one could organize this kind of hierarchy. And we see this thing in computer architecture routinely, right? I mean, our disks are slow, our main memories are fast, and cache is even faster, but we create a hierarchy. So we organize resources in a hierarchy and then just make sure that my computation or data or sensing or whatever is being done at the right resource at the right time. In processors, we kind of face that issue. We'll skip this slide. So one of the goals, one of the ways of thinking about these systems is that what I'm seeking is energy proportionality. So by that, what we mean is the following: that I want the power being consumed by the system, or rather energy being consumed by the system over some time duration, be somehow proportional to the work it is doing. That is, if I'm doing nothing, the system should not consume any power, and if I'm doing a lot of stuff, it should scale. And as you might imagine, we see that in our systems quite a bit, even our smartphones. So this is an example out here where every once in a while you're going to swipe something and all, there is some clock animation happening and all. So if you look at the workload in the system, there's a high degree of variance which is happening. And oftentimes the workload also depends upon the data you are facing. In fact, if for things like video encoding, decoding, image encoding and all, depending upon the content of the image or content of the video, the workload changes significantly, because a lot of these algorithms are sensitive to the actual value of the data. A blank image, flat color image would be a lot easier to decode than an image which has a lot of rich stuff, or like a video with a lot of motion would trigger a lot more computation than a video which is not much is happening. So there's workload variation in these systems, and somehow you would like to design a system where in the face of these variations, it scales proportionately, scales kind of nicely. So with this energy proportionality goal in mind, so what you want is a system which when I need zero performance, it's at zero. When I need high performance, it scales. So in essence, ideally, I would like a line which can start at origin and goes it's a linear system. But that's not how real hardware is. It's very hard to design things which are truly energy proportional. The reason it's very hard to design things this way is because our systems have lots of stuff which is just the penalty of the system being up. Okay, so there's a significant intercept right there. But the other thing is, it's very hard to design a system which can scale across a wide variety. It's kind of like saying, can I design a car which is great, very fuel efficient for city speed driving, and by the way, is also very efficient when I'm on the racetrack. Okay, so very difficult to design system because there's an architectural overhead which comes when you are seeking high performance. But within a particular range of device, you can still play games. So like if I have a processor, a high-end processor, it's designed for high performance, but as you see, it's not very energy proportional. Okay, it's kind of beginning to flatten out here. But within this, I can play games. So like one very common way to sort of achieve performance and power trade-off is something called dynamic voltage frequency scaling. So what this refers to is the following. I can always slow down a processor. Okay, so I need less work. I slow down the processor. If I slow down the processor frequency, so let's say gigahertz, I drop it to 500 megahertz, then the processor will consume less power, right? Because power is proportional to frequency. But I will need twice the time. So my processor is going to remain up longer, and therefore I will consume same amount of energy, right? I mean, I reduce the power, but I increase the time, so I can even out. So the way around that is that the frequency that with which you're operating, as you lower the frequency, you also lower the voltage, because for a given voltage, there is a maximum frequency you can sustain because it affects the speed of the electronics. So in DVFS, what we do is we coordinate the two. We reduce if I need less performance, I'm going to lower the voltage and I'm going to lower the frequency. And it turns out by the time you do all that combination, you have a quadratic or higher reduction in power. So that's great. So I have some degree of control between performance and power, or speed and power, within a particular architecture. So like this could be an A15 processor, for example. But the problem is this is a heavy processor, superscalar, multiple cores, stuff like that. It flattens out. So now to take care of this, the strategy then becomes I'm going to go heterogeneous. I have a big core and I have a smaller core. This is architecturally simpler. So so the cost of keeping this up is lower. So this is optimized for somewhere out here. And now, and I may have more. So the idea is by taking a union of these, I can begin to approximate that line that I want, which is something which is asymptotically zero at no performance. But I have to somehow figure out how to manage these things. But this basic idea in recent years has emerged. So ARM calls it big dot little, big processor, little processor. I think it has been used since Samsung S6 range. So kind of the idea is these are chips where you have multiple cores, but some complex cores, some simpler cores. I think Apple's chips are the same way, and Qualcomm's chips are the same way. So very sort of a way which has emerged in recent years. And so when we think of the processor, really at this stage, a processor is a collection of pairs of these potentially, okay, and multiple pairs of these, right? So like for example, the octa-core chip from Samsung was organized as 4 little cores and 4 big cores, and within each pair, you have to make a choice. You cannot have both up, okay? So you have one up or another up, okay? So your operating system is constantly kind of juggling with this thing, and as you can imagine, that is a reasonably process that is complicated by the fact that there is overhead in switching between these two things, right? There is stuff sitting inside this core. When you're switching over out here, what do you do, and vice versa? It would be desirable, of course, that the two be of the same instruction set as they are in this case, because otherwise the overhead would be even more. But even without that, there are a whole bunch of issues. When do you switch over? You switch over cost. You switch over too frequently, then it becomes a problem. So this OS has to do a lot of that legwork. But once you are able to do it, kind of the idea is that depending upon which mode you are in, either the big core or the small core will be activated. And prediction might help, because if I knew in advance what's going to happen to the workload, I can arrange for the right core to be made available. For example, let's say there's a burst of activity, and then if I knew the future that the burst of activity is going to come very soon, then maybe I'll leave the big core up and running, because otherwise the switchover cost is going to be an additional penalty. So there are all this complication ends up happening. Let's see, I'm kind of out of time, so I'm going to stop at this stage. We'll pick up this thread, but energy proportionality is a concept which applies equally well at embedded systems on one hand, and on the other hand, even at the data center scale. That is, you really want your power consumption to scale with the work that you do. Okay, so I'll see you guys on Monday. And meanwhile, I'll share the project idea thing, but it's still a work in progress. And if you have any other questions, I have an office hour from 4:30 to 5:30. So if you want to borrow against $25 deposit the embed,